the second talk of this afternoon, which will be like with Bruno Carneiro. He will talk about the semi-classical conformal blocks and black hole scattering. So, please.
Thank you. I guess first and foremost, I should thank profusely the organizers for the great honor of inviting me here, and for the loose definition they have of locality, since they think I'm a local boy. And my university is probably farther away than other people outside the country. Anyway, here you go. I'm going to talk today about my own idiosyncratic way to think about conformal blocks. I've tried the patience of most people, but so be it. And in the end of the day, I try to tell you why I think this is useful, among other things. Anyway, I guess everybody knows this, but here we go. Global conformal symmetry is a very powerful tool because it allows you to basically define an inner product and an algebra of operators, one of Wilson's dream, to define effectively the OPE between quantum operators. It fixes the 2- and 3-point functions between primary operators. It also gives a basis in which you can decompose 4-point functions in 2 dimensions. Especially, you can find this basis is called conformal blocks explicitly in terms of the parameters of the Virasoro algebra. And for our purposes here, it's good to keep in mind that it also depends on an extra parameter which has the interpretation of this intermediate channel. In this case, I'm writing from left to right, and from right to left, sorry. And this would be the S channel, conformal channel. Right, so there are many ways to compute the conformal blocks. Zamolodchikov themselves, they gave some recipes in the late 80s. You can write recursion in terms of the degenerate operators of the representation theory of Virasoro algebra. It also can give you recursions taking into account the analytic structure with the central charge, and elliptic recursions, and so on and so forth. There are many ways to compute this. One particular way, which would be interesting for me, would be using the AGT correspondence. I guess that I'm not going to make myself a fool trying to explain this very well, but you relate the conformal blocks to some instanton partition functions of n equals 2 super Young Mills with 2, well, 4 in this case, 4 multiplets in the fundamental. And you turn on some vacuum expectation values for the scalar. So you can give the generic structure here as a function of the conformal modulus, and you write this in terms of these functions z, which are sometimes called Nekrasov functions. One thing that I should tell you about here is that you have this nice interpretation of the conformal modulus as the holomorphic coupling of the super Young Mills, and also you have the vacuum expectation value to play the role of the Liouville momentum of this intermediate channel. So it actually plays a different role than the external Liouville momenta. So the Liouville momenta of the external operators. And this is somewhat artificial from the CFT point of view, but it's actually quite natural from the AGT and Seiberg-Witten. But it just goes to show that these different views about the conformal block can actually give you new insights. So the problem that I have particularly is to compute conformal blocks, and for reasons that will become clear later on, I will try to understand the analytic structure of the so-called level 2 null vector word identity, which is the third line of this slide. And this comes about because there's a degenerate representation of Virasoro algebra for particular values of the of the primary operators. It's also well known. And in this particular case, for m equals 2 and n equals 1, oh, sorry, the other way around, the null state should decouple from the rest of the spectrum, which gives you rise, if you write the action of the Virasoro algebra, how do I go back? Good. The action of the Virasoro algebra in terms of these differential operators, it should give rise to some partial differential equations, and this involving the correlation functions with some insertions and the degenerate insertion. In this case, it's a second order partial differential equation, and this fact that it's second order means that locally you can have, for a given value of this partial derivative, you can have two different linearly independent solutions. And you see here that the two linearly independent solutions, they codify really nicely the fact that the OPE between this degenerate operator and a genetic operator has two conformal families. Will be very important to us, the analytic structure here. Around z equals w, you see that this is a non-analytic function. You have a branch cut, and all the primaries that you have and the descendants will be analytic with respect to z. And likewise for this other family, although with a different scaling behavior near w. Okay. So going further with the analytic structure, I'm going to concentrate myself to the case where you have a semi-classical limit. Semi-classical limit is somewhat technical, in which you take the central charge to infinity. In my parameterization, take this parameter from Liouville field theory to be 0, at the same time as you take this conformal dimensions to infinity in a scaling limit. So I'm going to keep this small case delta here to be fixed. In this particular case, the conformal blocks is expected to exponentiate. So it means that the particular correlation function that we are defining will be written as some wave function times the conformal block itself. So the reasoning being, the physical reasoning being that the degenerate primary operator is light, and all the others operators that you have here are heavy because you are taking b going to infinity. Well, in this particular case, the intermediate channel actually becomes classical. You have a particular definite value for it, and then you can write the level 2 null vector condition that I wrote in the last slide as an ordinary differential equation with some particular coefficient for the wave function given by t here. T in this case is the classical expectation value of this stress energy tensor. And it's the two coefficients that show up here because the t is basically determined from the OPE between t and the primary operators. The coefficients delta are fixed by the conformal dimensions, and the coefficients c are computed as derivatives of the semi-classical conformal block. It's by abuse of language I'm calling semi-classical conformal block these w functions here. And the same thing that I talked about before also arises here. Because of the OPE between primary operators, the fact that you have the intermediate channel to be a definite value, this parameterized by this sigma here, means that I'm considering some particular solution of this differential equation with some definite intermediate monodromy. So I have some singular behavior between 0, t, 1, and infinity. And if I draw a circle around t and I let it continue the wave function psi, then I'm going to pick up a phase that's proportional to this that's parameterized, I should say, by this intermediate channel label sigma. So what does it mean? It means that I have some control over the analytic structure of psi, and solving the original level 2 null vector condition and try to, from that, trying to find this w function here has a deep relation between the analytic structure of psi and the parameters that enter into the equation. This is actually the original form of the Riemann-Hilbert problem, which originally meant to construct a function with some analytic properties given as a solution of a second order, in this case a second order differential equation with linear with at most double poles. I can go over the technical details later on. You actually can read them directly from the differential equation by just, instead of looking at the usual Frobenius solutions that we learn when you're learning mathematics at the beginning of kindergarten, perhaps, then you instead consider these flow case solutions, and instead of having analytic expansion around some point with some leading phase here, you have a generic Laurent expansion here that should converge inside an annulus that encompasses, in this case, the two singularities. The leading behavior here should depend on sigma. That's why I'm parameterizing that by here. And then the sigma here will pick up a phase as you go around this annulus. By hypothesis, I'm supposing that this Laurent expansion converges inside the annulus. So you can codify this parameter by monodromy matrices, and on generic grounds, these are a representation of the loop group of a four punctual sphere, satisfying this relation between them, because as you compose the loops, you compose the monodromies by matrix multiplications, and if you go around the four singular points on the sphere, you have a contractible loop. The way I'm phrasing this also has some ties with this theory of holomorphic connections. And here I'm trying to parameterize that in terms of the function t that I just defined before. And I'm going to talk a little bit about this A now. Hopefully I will have time to do that. The way to parameterize the monodromy is a good way to parameterize the monodromy is using these fetch and listen variables, and here I'm doing a very pictographic representation of this sphere with 4 points, and the fact that the composite monodromy is related by this sigma here. And it's actually, the Fenton-Nielsen coordinates are actually related to the an algebraic problem of trying to find two matrices, M2 and M1, that multiply to a diagonal matrix. There is some liberty in choosing M1 and M2, if you, but the liberty is actually only by conjugation by a diagonal matrix. And the parameter that relates the conjugation of the diagonal matrix, I'm going to call eta. There is a symplectic structure in this space. If I keep thetas fixed and try to see sigma and eta as two variables parameterizing the space, I can actually define a Poisson bracket between these two, in which the sigma and eta are double coordinates. This is called the Goldman bracket, and this goes to the theory of representations of this monodromy group since the 80s. So, on the other hand, the parameters that enter into the t function that I defined before, so it are parameters that enter into this holomorphic, the holomorphic connection here. And these are also, the space is also a symplectic space and has a symplectic structure given by the Atiyah-Bolt form. And in this Atiyah-Bolt form, C and T, the parameters that enter into in this case, there is only one conformal modulus and only one accessory parameter C, are also double coordinates. It's actually, it's not a trivial exercise, but I'm not going to go into that. And so in this way, you can see the conformal block as the generation function of the symplectomorphism between the monodromy parameters and the connection parameters. There are many ways to compute them. As I told you, you can actually, there is a very numerically efficient to compute that using the relation between the parameters sigma and eta from the differential equation themselves. This is called Hill's method or continuous fraction method, and it has been known since the 1930s when people were considering the spectrum of helium. And this will come back in some moment. I have 10 minutes, right? Okay. Okay. Great. This is given by a continuous fraction and defines the relation between the parameters sigma and c here in an implicit manner. There is a question whether you can invert this relation, and locally you can. If you invert this relation, you find the usual expansion for semi-classical conformal blocks, and actually it's a very efficient way to do so. You can go up to 1,000 levels without any effort, of course using mathematics, not doing by hand. If you integrate this, you can find the conformal block itself up to some constant. You can define this constant here, this function, constant factor, not dependent on t, using other methods. But this of course only gives a local expansion for the conformal block, and I'm trying to tell or understand anything about the global structure of this. Global structure, by global I mean global with respect to the parameter t. And in order to do that, I need to resort to yet another way to understand the conformal blocks, and this comes for isomonodromy. This is actually a piece of beautiful mathematics from the beginning of the 20th century. I won't have time to go over that, but basically it deals with the formations of this first order differential equation. And here you can see that you have some coefficients. These are, I'm trying to see these coefficients here as 2 by 2 matrices. And generically, they are functions of this WK here, which are the positions of the singular points of this differential equation. You can actually complement this differential equation with respect to this function, to the parameter W, by another set of differential equations with respect to the parameters, the positions of the poles, WK, and by trying to make a well-defined function solution phi, so in such a way that the derivatives commute, you arrive at the Schlesinger equations. So these are compatibility. You can see that as zero curvature equations, so I guess that qualifies as some integrability. And this has been known since the 20s to define flows on the space of parameters A. For in my point of view, phi here will be a 2 by 2 matrix, and I'm going to see A as some holomorphic connection. This is first order, not the second order that I had before, but they can be related by a gauge transformation I'm not going to go into. The interesting bit about this flow is that it's Hamiltonian. There is a tau function generating the flow, and the tau function is easily computable in terms of A. And the tau function itself was solved in a beautiful series of papers by Lisov, Yorgov, Gamayun, and some other collaborators. And for my purposes, this is given as in terms of Fredholm determinants by this paper by Gavrilenko and Lisov from 2018. Fredholm determinants are very interesting from the numerical point of view because they give a numerically stable ways to count it. So they also give a formula, also written in terms of Nekrasov functions, but in a quirk. It's not given by semi-classical Nekrasov functions. They are given by C equals 1 conformal blocks. And the expansion has this structure here. It's a double series. There are some strong theorems saying that this is a holomorphic function on the complex plane if you discount t equals 0, in this case 1 and infinity. And in terms of the tau function, you can actually write the coefficients, sorry, I have to go back. Write the coefficients of the differential equation that I had originally, C and sigma, in terms of, go forward, in terms of the logarithm derivative of the tau function, and a condition that can, by the Hirota equation, be related to the zero of an associated tau function. So this actually helps me defining the conformal block, at least this accessory parameter globally. By using the braiding relations of the tau function, I can first of all, find this constant function f in terms of integral of log derivatives of Euler functions. I'm showing them explicitly, sorry for that. These log derivatives can be written in terms of Barnes functions. And because of the symplectic structure, I can also relate the eta to the derivative, this should be sigma, sorry about that, to the derivative of the semi-classical conformal block. The odd thing here is that now interpreting this as the first condition that I have there, if you compute, if you are given a semi-classical conformal block and you compute eta in this manner, you automatically find a zero of the tau function. Zeros of the tau functions are interesting for other reasons that unfortunately I won't have time to go into. Anyway, you can use these braid transformations to study the expansion of the conformal block at different points. And not only you have the symplectic structure here, but you can also relate the symplectic structure at different points of t, because each one of these monodromy parameters, zeta and sigma here, they are related to each other by some by some symplectic transformation in the space of monodromies. So in this sense, these expansions, they are expansions of the same function. Should go forward, right. I also should note everything that I talked about here, I talked about regular conformal blocks. Everything also works for irregular conformal blocks. There are a very effective way to compute them, and either at 0 at infinity, but in this case the monodromy parameters, they have to be taken care of very carefully, because the relations between them involve some functions which do not have a very definite limit as they go to infinity. Anyway, you can also compute the expansion at infinity parameter, and there is some strange, I'm going to talk about them generically in these F0 terms again, and there is some strange connection between the two expansions that probably is related to resurgence. This is actually tested to order T250. I think they have a E2 for that. Okay, so in the 2 minutes that's left, I'm going to talk a little bit about physics, actual physics. And I got into this because I was interested in solving black hole linear perturbation theory. One thing that I did not tell you is that you can actually compute not only the monodromy properties of a solution of the differential equation, you can also compute the connection between expansions at different points. And these people at CISA, they have this very nice formula in terms of semi-classical conformal blocks. The people have talked about this as the Trieste formula. And this also underlies the necessity of effectively computing semi-classical conformal block. This work, by the way, has been done with my former student, João Paulo. I hope he got a job soon. So linear perturbation theory is actually something very easy. I mean, I'm just going to skim through the details. You have basically linearized Einstein's equations, four-dimensional background corresponding to a Kerr black hole. And you can reduce these two differential equations as equation that of the type that I talked about, albeit with the irregular conformal block at infinity. This I'm going to interpret this as this level 2 null vector condition, and I can use the monodromy parameters to solve not only the angular equation by phrasing the eigenvalue problem as a monodromy condition, and I can reproduce data in the literature, but also the radial equation, in which the monodromy parameters actually have very nice interpretations in terms of black hole thermodynamics. This is actually the amount of entropy the black hole intakes as a quanta of energy omega and angular momentum m is absorbed by it. Anyway, the singular points of the radial equation also have a nice interpretation. They are the Killing horizons of the geometry. And you can phrase the conditions for quasi-normal modes, the excitations of the field which are localized near the black hole, also in terms of monodromy. This sounds daunting, but it's not actually, it's actually manageable. You can actually treat with that. Numerics match. These are, you probably can't see that, but there is a blue line here corresponding to the numbers that we've got, and the red line here corresponding to the literature, and we can see any difference between them. It's 10 to the minus 10 to the best literature numbers. You have nice behavior of this as you get to the extremal point or extremal black holes. There are modes which live for a long time. They actually live for infinite time as you get to the extremal limit. There is always the possibility of these modes becoming unstable as you take on non-linear corrections to this analysis. You can do it for a variety of Rice and Nordstrom black holes. You can find a very nice transition between modes that are damped as you go to the extremal point. So the imaginary part of it goes to a non-zero value, and modes that are undamped as you go to the extremal point, the imaginary part goes to zero exactly as you get to the extremal point. You can pinpoint these points of bifurcation easily, and you can also study the extremal black hole also using confluent limit of the tau function I just talked about. You can do expansions using the expansion of the conformal block for large parameters, for large conformal modulus T, and extracting numbers from this, you see that it matches the spectrum that you have for excited modes of the black hole. And you can write this nice phase diagram here, because you can understand this sort of a thermodynamic system in which you have the longest lived mode to be the fundamental mode, exactly the same as the Schwarzschild, but there is a critical line. As you pass through it, there is the most, the mode that lives the longest, the mode with the smallest part of the imaginary part. Becomes what's called the n equals 1 in Schwarzschild point. This red line here is discontinuous. There is some stable modes. In this case, this is the mass of the perturbation, and there is a crossover region here. So basically, it means that the tau function is rich enough to encapsulate all this rich physics. And so I'm going to finish before I'm kicked out. I'm just trying to convince you that studying the global properties of irregular conformal blocks are useful for CFT, sure, but they are useful for many other problems. I just talked about one of them here. This comes to a larger program, I think, from n equals 2 to try to quantizing the Seiberg-Witten curves. And actually, this is given as a procedure using the methods that I'm talked about here. You can study, particularly for black hole physics, study quasi-normal modes. You can also study quasi-bound states, although I haven't talked about this. One question that remains is whether you have to take these CFTs that I am trying to interpret them, this radial and angular equations from. They have to be taken seriously, because I haven't talked about that, but the momenta, the Liouville momenta associated to the radial and angular equations, they correspond to unitary Liouville Liouville vertex operators. So perhaps there is some more physics to be learned into that. There is a strange property of these systems in which you derive the accessory parameter for the angular equation, and that gives you this angular eigenvalue, and you feed that into the radial equation. So there is some sort of relation between the two equations, which would be understood by people that study tau functions in statistical mechanics setting as some equilibrium condition between two systems. This is compounded by the fact that the tau function has a formulation as a Fredholm determinant, so you also get the eigenvalues as a sort of circular equation involving a particular integral operator k here. I wish I could say more about this. The procedure that I've talked about here of solving the Riemann-Hilbert map, this map between parameters on the differential equation and monotomous parameters of the solution, has many other applications. I didn't talk about, but some limits that we cover the 6 vertex models. The Rabi model in quantum optics is also solved by this, and something that I like to call constructive conformal mapping, in which I'm given some graphical representation of a domain, and I use this machinery to construct the map between this some particular domain in the complex plane to the upper half plane. And well, I talked about quadratic differentials. Here is something I'm trying to learn right now. Last but not least, you have some aspects of resurgence here that I couldn't talk too much about, but would like to understand more. And I give you the dragon, the snake. I'm ready for questions if you have any.
Thank you very much, Bruno. Questions?
Yeah, thank you for the interesting talk. So you mentioned these flat column determinants and the tau functions. Do they appear? Are they specific to c equals 1, or
it depends. It depends on how you take it. They are usually defined to be tau functions or the isomonodromic system, and they are written in terms of c equals 1. The expansion is written in terms of c equals 1 conformal blocks.
So how does B enters into the flat column determinants?
Sorry, can you repeat that?
B, the parameter B, or C.
Yeah, C equals 1.
Charge. Yeah, no, but do you have them at arbitrary B? At arbitrary central charge?
No, I don't. This is considered in a paper by Teschner and Yorgov and Lisovi from 2016, I think. And in that paper, they talked something about, something that I understood as a quantum version of the tau function. What is that? Well, it's basically the promotion of this sigma parameter, this internal channel, to an operator. And then they write something about that. I don't know how far that program has followed since then.
Okay, and I was wondering about the mapping between the parameters of the conformal blocks and the parameters of the black holes.
Oh yeah, right. This is actually nice. This is actually nice. So for the radio equation, this is the map that gets there. You have some relation between the parameters of sigma and eta. So if you remember your Seiberg-Witten theory, you have some relation between the vacuum for the electric background and magnetic background, and that comes as this quantization condition. The parameters, the external Liouville momenta, they are given in terms of these thetas here. And you see that there is a real part. The real part is just a spin of the perturbation. Genetically, you have a spin integer up to 2. And the imaginary part has 2 bits here. The first bit is the frequency of the field. So this is the energy of the field. So it's the energy that's absorbed by the black hole. And this thing here is some genetic potentials. In this case, it's just the electric potential, because I'm talking about a charge field with the black hole. But if you have a curved black hole, yeah, here. This is just the angular momentum, and this is the angular rotation of the black hole. And you see that this is the temperature. If you go back to the papers, to the fundamental papers of black hole thermodynamics, this is exactly the intake of entropy of the black hole as it absorbs the quantum of the field, divided by 2 pi. So basically, Liouville momentum is equal to the intake of entropy. I wish I could tell you something more, something deeper about that. Okay.
More questions? If not, let's thank Bruno for the very interesting talk.
Thank you.
Okay, so if you were not here in the morning, I had announced that I'm happy to organize a few music-related stuff. We will put it on. Tiago, podemos pôr lá o slide do samba? Por favor, obrigado.